Are there objects that are so distant that the light travelling from them began its journey close to the Big Bang itself? Is that possible? And the answer is yes. And that light was first detected in the 1960s. It's called the cosmic microwave background radiation. So essentially the idea is, how far can I look in every direction? You can look about 13.8 billion years into the past, back to the origin of the universe. It's on this diagram here. It says afterglow light pattern, 380,000 years after the Big Bang or so. That is the furthest we can see. What happens if you go at the speed of light? Well, special relativity, Einstein's theory, is built such that the distance between any two events in the universe along the path of a beam of light between the events is zero. No time at all. That's the way that Einstein's theory is built. So he asked the question when he was younger, famously, what would the universe look like if I travelled alongside a beam of light? And the answer is that you wouldn't perceive any time. If you've got any mass at all, you can't do that. You can't go at the speed of light. But if you've got no mass, you go at the speed of light. So if you're a photon, you go at the speed of light and no time. If something falls into a black hole, then ultimately, in some form, it comes out again in the far future. But by that, I mean in the same sense that if you take a book and set it on fire, right, and burn a book, then if you could, in principle, collect everything, all the ashes and the light and everything that comes off the book, then in principle, you could reconstruct it. And it seems, we're pretty sure it's the same for black holes. You throw the book into a black hole, from the perspective of the book, we think, you fall across the horizon into the interior of the black hole and go to the end of time, basically. The book essentially goes to this thing, the singularity at the end of time. From the external perspective, we think that the book gets vaporized on the horizon, and we think that both pictures are correct.
What are your thoughts on alien life, on life outside of this planet?
I think there must be. Even in the solar system, I would not be surprised if we find microbes on Mars or on some of the moons of Jupiter or Saturn where there's liquid water.
Like Europa.
Yeah, and the reason is, if you think about, if you look at the history of life on Earth, then, so Earth formed, and it was just there was no life. It was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. Somewhere along the line, geochemistry, active geochemistry, became biochemistry on Earth. Why is time different on different planets, like in Interstellar? So that's an easy question to answer. It's Einstein's theory of general relativity. As you come closer to a planet, then your time, so let's say you have a watch and you look at the watch, then you'll see the watch tick at the normal rate, 1 second per second, and you won't see anything unusual. But from the perspective of someone far away, that watch will be ticking more slowly than their watch. And it's really to do with the distortion of space and time in the vicinity of the planet. So the general rule is, if you go to something that's very massive, so you approach a very massive planet or even a black hole, then as you go there, from the point of view of someone far away, they will see your time tick more slowly. An argument with Neil deGrasse Tyson about lightsabers once, because I claimed that in principle they're possible. And he was trying to say that they aren't, but they are.
Would it have to loop back around because the light's not continuing to, like, the fact that it goes to a certain distance and pauses?
Well, you'd have to have a mirror or something, I guess, yeah.
Something
That's
would have
true.
to be the end of it, right?
That's true. So it'd be a different kind of lightsaber. The only point I was making is that photons, particles of light, can bounce off each other. So we see that in really high energy experiments in particle accelerators, we can collide photons together. It is true that light can bounce off it. Can hit light, but at very, very high energy. Is time travel possible? It's kind of obvious to say it's possible into the future, because of course that's what we're doing, we're moving into the future. It then gets interesting because you say, why do we have to go into the future? Why can't I stop going into the future? Well, you can vary the rate at which you go into the future relative to someone else. For example, if I was to get in a rocket now and accelerate off, even at 1g, right, just a sort of acceleration I could take, and head off and end up traveling relatively close to the speed of light, and let's say go to the Andromeda galaxy, which is 2 million light years away from the perspective of the Earth, and then turn around and come back again. If I go close enough to the speed of light, I could arrange it so I would age, let's say, a year on the outward journey and a year on the inward journey. And you could do that calculation. But 4 million years would have passed on Earth. So I would come back on that journey 2 years older, but I'd arrive at the Earth 4 million years in the future. We don't know how the universe got into the state that we call the Big Bang. So we don't know whether the universe existed before that. We have theories that it did, theories called inflation inflation, which are very popular theories. You'll find them in all the textbooks, which say that before the universe was hot and dense, which we used to call the Big Bang, space and time is still there, and the universe is expanding extremely fast. It's called inflation. And then that period draws to a close, and that expansion sort of slows down and almost collapses and changes. And the energy that was driving the expansion gets dumped into space and changes and ultimately makes the particles out of which we are made. That's actually the standard model of cosmology now. So we do have an idea that we redefine the Big Bang as the hot Big Bang, and it's not the origin of the universe in time. It's the end of inflation. The universe behaves like a quantum computer. If you're playing a computer game, then there's kind of a reality there, right? But it emerges from just bits of information. We think that in some sense, and I keep saying in some sense because we don't know, we don't have the language, but there's a sort of a network of bits, qubits, quantum bits, and that may be a description of the world, including ourselves and space and time. And this kind of emerges out of this network, which looks a bit like a quantum computer. That is not to say that I'm saying we live in a simulation. I'm saying it looks a bit like the universe has a description which is similar in a sense to a quantum computer.
Not every star becomes a black hole at the end of its life?
No, something like the sun. When it collapses, there's a force which is caused by electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. So as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way. And that makes a force which holds them up. That creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. That's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. They move faster and faster. So if it's massive enough that it overwhelms the electron thing. One of the great unsolved mysteries in biology, we seem to be, all complex creatures seem to be, we're called eukaryote, which is cells with a cell nucleus and all that kind of stuff. And they look like they're the merger between two simpler life forms, a bacteria and a thing called an archaean. So it looks like somewhere in 2 billion years ago, whatever it was, in some ocean, the bacteria cell got inside the archaean and survived as a symbiotic organism, essentially, and then somehow, unbelievably, managed to reproduce and replicate in that configuration. And that does seem to be the origin of all complex multicellular life on Earth. What happened before the Big Bang? If you define the Big Bang really carefully as the time when the universe was very hot and very dense, our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. We have no evidence of alien civilizations at all. That might mean we haven't looked hard enough because we haven't looked particularly hard. The galaxy is very big. But it might also mean that civilizations are rare. It took 4 billion years to go from the origin of life to a civilization, which is about a third of the age of the universe. And if you start to say, well, if that's typical and we don't know, then it may be that there are very few solar systems and planets and stars that are stable enough for that long to allow for evolution to do its work and for the single-celled things to go to multicellular creatures and plants and make an oxygen atmosphere and then make a civilization. Brian Schmidt got the Nobel Prize for this discovery. He told me once, I don't know if I told you the story before, but he told me that he made this measurement, and it wasn't really, he was looking at supernova explosions, and he'd seen that the suggestion in the data was that the universe is accelerating in its expansion, not slowing down, but speeding up in its rate of expansion. No one was expecting it, so he thought it was just wrong. But he couldn't find anything wrong with his data. So he published it and thought, well, that's the end of my career. And there was no mistake, and he won the Nobel Prize. There's a thing called the Fermi paradox. Let's say trillions of planets in the Milky Way. Milky Way's been there for over 13 billion years, pretty much the age of the universe. If there's no one else out there, then the question is why? Because there's been so much time and so many places for civilizations to become spacefaring civilization. As Elon talks about multiplanetary civilization, we're very close to becoming a multiplanetary civilization. And once you have become a multiplanetary and multistellar civilization, if you become that, you're immortal, basically. The question is, the paradox is, why does it appear nobody has done that? You take the sun, our sun, 700,000 kilometers in radius, and squash it down until its radius is about 3 kilometers. You can imagine doing that. then the gravitational pull at the surface is so strong that nothing, not even light, could escape. So that's the basic idea behind a black hole. It's a region of space from which nothing can escape. I don't believe in a God. However, I don't like the antagonism. I mean, what you can say if you're a cosmologist, what you should say, we know that the universe was very hot and dense 13.8 billion years ago. We don't know how it got hot and dense. We don't even know, actually, if the universe had a beginning in time. Don't know. That, to me, is where the science starts.
Science doesn't rule out the existence of a creator.
No, but in the sense that I just said, that I think we're overstepping the mark. I do not believe there's any evidence for a creator. However, there certainly isn't no evidence. The point is that the correct thing to say is we don't even know whether the universe had a beginning. I don't even know whether it was eternal. Nobody does. That was the point I was making. I think we're stepping into an area where we don't really need to be. They call it the Great Silence. The Great Silence. And it's a tremendous mystery, as I said earlier. But it does seem that the universe is quiet, as far as we can tell. You could say, well, what if the civilization that evolved is far ahead of us? What if the space probes are the size of an iPhone? Well, it's kind of a reasonable thing to say, actually. Because why would you not, if you can build a little thing,
right?
It's easier to send around the galaxy than a big thing.
Yeah.
So why would you not, as you said, these ultra intelligent quantum computers, why would they not be tiny? So you could say, well, that maybe they are. Maybe they're all over the solar system, but they're the size of phones, and we wouldn't have seen them. We're just saying that the way that we've looked for energy signatures, for example, of civilizations, we tend to look for big things because that's all we can see. And we don't see any big things. We don't see any big structures. We don't see any evidence of spacecraft and all that kind of stuff. We also detected a collision between neutron stars using the gravitational wave detector. And we pointed optical telescopes at that collision and saw the signature of gold being manufactured. It was always a question. We used to just think, well, it comes from supernova explosions. But it also seems now that it comes from the collision between neutron stars. So one of the reasons that it's very rare is because it takes rare processes in the universe to actually make it. You look at the gold, your wedding ring or your watch or whatever it is, some of those elements clearly came from the collision between neutron stars at some point before our solar system was formed, which makes it more wonderful.
Well, every human being is a carbon-based life form, and carbon comes from
stars. Yeah, as Carl Sagan said, star stuff.
That's the craziest thing ever. Like, you need a star to blow up to make a person in the first place.
It's a remarkable thing.